In this lecture, let us continue our discussion on digital filter structures. So we had started a discussion on digital filter structures and we considered the problem of analysis. One can write the equation and then eliminate the intermediate variables to get the overall transfer function. Like if you remember in the last lecture, we introduced two intermediate variables, v of z and w of z. You can replace these intermediate variables and then you will get the overall transfer function y of z divided by x of z, and this is called h of z. Now on the other hand, the synthesis problem is tougher. Okay, so the synthesis problem is tougher than analysis problem, and as I said, the synthesis problem, one of the characteristics is that if there exists one solution, then there will exist an indefinite number of solutions. Okay. So one must remember this for synthesis problem. One can argue, if I get one solution, why don't I stick to it? Okay, see, if one solution exists, why can't I satisfy with that solution and finish it off? Why do I go for alternative solution? It turns out that different structures have different properties. If you find one solution and for that solution if you analyze or if you try to find things, then it has different properties, and the two things that we have to worry about is overflow and then word length effect. So every solution has its own overflow problem and word length problem. And now overflow, let us see what it is. If at any stage in the filter there is a situation, then there will be a overflow and the filter will cease to perform in the manner that you like it to perform. Okay, so if whenever the overflow occurs, then the filter will not perform properly the way you like it. And then word length effect. This problem is very important problem, that because of finite number of bits that you have to use. Okay, so you may use 8 bits or you may use 16 bits or you may use 32 bits, and therefore of necessity the coefficients as well as the signals have to be truncated. For example, you take an 8-bit number and multiply by another 8-bit number and this multiplication of this to 8-bit number will give you a 16-bit number, right? And if your hardware is 8-bit, then you will have to truncate to 8 bits. So if you do that, then there will be a problem. That problem is called a word length effect. And if your hardware is 8-bit, then you have to truncate to 8 bits. So various structures have different properties with regard to word length effects, and one should choose the one which has the lowest quantization error. Okay, you choose a structure such that structure has the lowest quantization error, and this is the reason why multiplicity of structures have to be worked out before making a choice of an optimum or a near optimum structures. Even though you have many structures, you have to choose the one which has the lowest quantization error. And in the last lecture we also showed how to derive two structures for the transfer function P0 plus P1 Z inverse divided by 1 plus D1 Z inverse, and we showed that one can make the structure canonic with respect to multipliers with respect to delay. We will expand on this today to see how a general IIR transfer function can be realized by a canonic structure. When I say canonic, what I mean is canonic in both delays and multipliers. But before we start IIR, before we start with IIR structures, let us introduce the topic of transposition. So this transposition is an important topic, and this transposition allows one structure to be converted to another. So why are we converting this structure from one structure? Because we would like to study the word length effect and overflow. So this transposition is very much useful to convert the structure from one form to another form. Okay, and to convert from one form to another form, and that process is known as transposition. And this transposition can be explained with a reference to let me take the same example with a reference to this example P0 plus P1 Z inverse divided by, let me take 1 minus dz inverse. In the last example we took plus, but just for a change I am taking minus here. Okay, so I am taking minus here to bring variety into experience. Let us change the transfer function a little bit, and instead of plus I have taken minus here. Okay, instead of plus we put a minus. Now if you remember the structure, let me draw that we have drawn in the last lecture, x of z, then this is given to a summer, okay, summation, and then z inverse, a feedback through multipliers. This is d1 like this, and it would be d1 now. Okay, not minus d1. Please be careful because I have taken the minus sign here, negative sign, therefore this is positive sign here. And then we have two multipliers, P0 and P1, okay, and output of which added together to give you y of z. Don't forget to put the arrow mark. That's it. So this is a canonic structure, canonic in multipliers, and it is canonic in multipliers. Why? Because I used only 3 multipliers. Okay, first multiplier, second multiplier, and third multiplier. So in the given expression also I have only 3 multipliers. Okay, so we need only 3 multipliers here, and only one delay because it is a first order filter, and therefore this is canonic in multiplier as well as delays. Now in this structure, if we make the following changes, so first interchange the input and output. So note down the steps very carefully. Interchange the input and output. What I mean is, this is going to be now the input and this is going to be the output. And the second point is reverse all the arrows. All the arrows. Okay, so if it is this direction, then make it in the reverse direction. Now the third point is, as soon as you reverse the summation node, wherever you find summation node, replace the summation node by a pickup node. Okay, and pickup node is replaced by summer or summation node. So these are the three steps that we are going to follow to find the transposition. All summation nodes are replaced by pickup nodes and all pickup nodes are replaced by summation nodes. Okay, now if you look at the figure here, see, this is the pickup node. Okay, so this pickup node becomes summation, and this is the pickup node, and again this becomes the summation, and this is a summer, that summer becomes pickup node, and here is a summer and that summer becomes pickup node. That's it. So this is what we will do to transpose the given structure. Okay, so if you do that, then you have transposed the structure. So the transposition involves generally 4 steps. The first one is interchange the input and output. Interchange the input and output. And the second step is reverse all the arrows. And third one is replace each summer by a pickup point. And the fourth point is replace the pickup node by a summer. So these are the 4 points that one has to follow. Okay, now I need some space. Let me delete this. So here the first point is input becomes output and output becomes input. Interchange the input and output, right? So therefore this is my y of z and this point is x of z replaced. And now this is the summer. So that summer becomes now a pickup node, and here I have a summer, that summer becomes a pickup node here. Okay, and here I have a pickup node that becomes a summer. That's it. Now connect it and reverse the arrow mark. So you put the arrow mark like this, and then you put like this, put like that, and then as usual, so D1, and this will be a summer, there is a delay, and then multiplier P1 like this, but in between there is one more multiplier. Don't disturb the multiplier and all. P0. Okay, change the arrow mark, so it becomes like this, then it goes like this. Now it is upward arrow mark like that. That's it. So you will have y of z here, x of z here. Arrows have been reversed x of z is now multiplied by, this is x of z, right? X of z is now multiplied by p0 in this direction. Signal flow is in the direction of right to left, and x of z is also multiplied by p1. Okay, then from this point, from here, the multiplier d1 comes in this direction, and since I have not two signals coming, one signal is here and one signal is here, so I put a summer here. Okay, therefore the pickup point becomes a summer here, and then z inverse. So z inverse goes from the summer, then naturally we have summer here. It comes like this. Okay, now one more point I would like to mention here. Conventionally, when we draw the diagram, we always put x of z in the left hand side and y of z on the right hand side. Okay, output on the right hand side and input is on the left hand side. So if I flip this diagram, this structure, then it looks like this. So P0, P1, then this is, and this point is y of z, and this is multiplied by d1. Okay, you put a summer here, and then z inverse, or else let me draw it a little bit. P1, and you put a summer here, and then here you put another summer and another multiplier d1, a pickup node, and goes like this, and there is a delay z inverse. Just I flipped the diagram. Okay, the same diagram, but I flipped the diagram so that the input is on the left hand side and the output is on the right hand side. Okay, so P0, P1, summer, z inverse, that's it. So this is transpose of the given structure. That's how one will do the transposition. Now again you can verify this. Okay, so you can write y of z divided by x of z and you can find out. If I want to find the transfer function, we have to show that this structure gives the same transfer function as this guy. You see that y of z, if you look at this transpose structure, y of z is equal to this point. So let's say this is point A, and point A is summation of these 2 points B and C. What is B now? B is P0 times x of z. And what is at point C? Again 2 signals. Okay, this signal and this signal, and in this point you have P1 times x of z, and in this point you have D1 times y of z. This D1 times y of z and P1 times x of z both are delayed by one sample. Okay, so P1 z inverse x of z plus D1 z inverse y of z. Now if I take this term to the left hand side, then y of z multiplied by 1 minus d1 z inverse is equal to, on the right hand side you take x of z commonly outside, so p0 plus p1 z inverse. So y of z divided by x of z is equal to p0 plus p1 z inverse divided by 1 minus d1 z inverse. And this is the same that we started with, and this is in general true. Given any digital filter structure, you can always make a transposition to get an alternative structure. Okay, alternative structure also has the same transfer function, but what is the difference? The overflow and word length effect may change. Okay, even though these two structures, the original structure and the transposed structure, have the same transfer function, but they may not have the same properties. When I say properties, what I mean is overflow and word length effects. So therefore overflow and word length effects are different. That is the very important property one has to remember. For that reason only we are transposing the given digital filter structure. And ideally, if we had infinite bit arithmetic and infinite storage capacity, then the structures would have been the same. Okay, so no need to worry about overflow and word length effect and all, if you use infinite bit arithmetic and infinite storage capacity. But in practice that never happen. But in practical implementation they have different properties. In theory they would have been the same, okay, because the transfer function is same. For transposed structure, this is the transfer function, and normal structure also, this is the transfer function. There is no difference. So in theory no difference, right? In theory they would have been the same, but in practical implementation they have different properties. When I say properties, what I mean is overflow and the word length effects. And therefore it is worthwhile to determine transposed structures. Okay, now let us okay, that's it about the transposed structures. So let me stop at this point. In the next lecture we will start FIR filters, okay, finite impulse response filters, and then IIR filters, and then I will give you a couple of examples where one can transpose the given digital filter structures. So let me stop here. Thank you very much.